Hey everyone, today we're looking at the problem find the sum of the power of all the subsequences. This was a hard problem featured in Biweekly Contest 126. During the contest I wasn't able to solve this, but I went back and upsolved it and want to share my solution with everybody. So this question says we're given an integer array nums, we're given the length n, and also a positive integer k. The power of an array of integers is defined as the number of subsequences where their sum equal to k. We want to return the sum of the power of all subsequences of nums. This is very important, and make sure we understand this. Then at the end, we just return it mod 10, 9 plus 7. So an example might make this a little bit clearer. So here we're looking at the case 1, 2, 3, where k equals 3. And essentially what this means is that we want to find all the subsequences that are part of this array that has a sum equal to 3. So here it shows 5 subsequences, but note that this example is only showing the subsequences that have a non-zero power, meaning it's only ones where they have some subsequence where k equals 3. To find all the subsequences of this array, there'd actually be 8 of them, because there would be 2 to the n and 2 to the 3. So for an array of size 3, we would have 8 subsequences. So let's keep that in mind. It'll be useful later. So here, let's look through this example. So the subsequence 1, 2, 3 actually has 2 subsequences with a sum equal to 3. So we have just the 3, and then we also have 1, 2. The subsequence 1, 3 has 1 subsequence with sum 3, just the 3. Subsequence 2, 3 has 1 subsequence with sum 3, just the 3. Subsequence 1, 2 has 1 subsequence with sum 3, 1, 2, and subsequence 3 has 1 subsequence sum 3, just the 3 itself. So as you can see, we're kind of doing a thing where we're getting all the subsequences of this array and then further looking in those subsequences for subsequences that have the sum of k. So it's kind of like this nested recursive subsequence kind of thing, which is really tricky to figure out. But after making some observations, you can kind of start thinking about this a different way. So one thing to kind of notice is that certain subsequences are counted multiple times. So look in this case, we have 1, 2 counted here, and we have 1, 2 counted here. We also have this 3 counted several times. So we have 3 here, 3 here, 3 here, and 3 here. So you can see this adds up to our total of 6, our solution, but we see that we're actually doing some kind of repeated steps to find all these subsequences. And really it's only 2 distinct subsequences, but they appear in different ways. So let's try to think of a simpler way to solve this. So I just want to expand on this example a bit more. So here, this is all the subsequences that we can create from this array 1, 2, 3. So you see we'll have our empty subsequence as well as all the subsequences we can actually generate from that array. And let's kind of think about what happens. So looking at these subsequences, we have 3. So here we know we have one subsequence where we have k equals 3. Right here. Here we have 1, 2. Here we have 3 again, second time we've seen it. Here we have 3 again, the third time we've seen it. And here we have 1, 2, second time we've seen that, and also 3. So as you can see, this is kind of redundant. What if we kind of switched our thinking to say, once we've found some sequence of numbers that equals to k, can we count how many times it contributes to another subsequence? Well, let's kind of think about it. So say we have the subsequence 1, 2 that we're looking at, right? We see it's 2 elements out of a total of 3 in our original array. So how can we figure out how many subsequences that this 1, 2 might be a part of? So we know that our total length is 3, and our length here is 2. So how can we use other elements that are part of this array to make our full array? And this might be a little confusing, so we'll kind of walk through it. So we have 1, 2. What other elements are in our array? So we can use 3, right? We can add a 3 here to become 1, 2, 3. Or we can leave it out. You just have 1, 2. So in both of these subsequences, we have subsequences that sum to 3. We have this here and this here, right? We see this is included twice. Let's look at another example. So say we just have our 3. What other elements can we, other subsequences can we create using this 3? So we have 3. We can add a 1 to have 1, to have 1, 3. We can do 2, 3. We can include that 2. We could have 1, 2, 3. Really just like considering every other possible combination of elements that can go with this 3. And we're doing this because we saw we're actually counting these subsequences with some k multiple times. So instead of generating all these subsequences, then going through and trying to count them again, we're just going to generate these subsequences and figure out how many times they fit into other subsequences of the array. And how do we do this? So there's kind of a tricky intuition that you have to come up with. So basically, if we're given any array, we know that the number of subsequences we can make is 2 to the n, right? With n being the length of our array. So say we're looking at a subsequence like 3 here. This is 1 out of the 3 elements. And we're basically trying to figure out, if we have this subsequence, how many other subsequences of this array can this be a part of? So if we take our 2 to the n, and we subtract the length of our current sequence, that will actually give us that number, right? So here, if we have 2 to the 3 minus 1, we have 2 squared equals 4, and we see that correlates to these 3's up here. Likewise, if we're looking at this 1, 2, we can do 2 to 3 minus 2 equals 2 to the 1 equals 2. And that will give us our 6, which is a solution. So this was a big leap of logic to make, right? You have to be able to really figure this out in order to solve this. And then once we realize this logic, what this really is an O1 knapsack problem. So we want to do the classic O1 knapsack where we make the choice to both include an element and not include an element. And basically by doing that, we'll generate this whole list of subsequences, and then we'll do this logic here to count the number. And we're going to do this in O of n squared times k time. So we're going to go through each index in the array, which is n. Then for each n, we also need to keep track of the current length of our subsequence. And then also k, where k is our sum. So you'll see when we implement our recursive function that these are all going to be inputs to our recursive function. So we could have any combination of these elements happening. So we have to account for those in our time complexity, and the solution is going to be an O of n squared times k solution. There are some optimizations, but I'll leave those for further videos. So let's hop over to the code and kind of walk through and see exactly how this works. So you can see here, I've set up this recursive function called findSum. This is going to take 3 arguments. So first we'll have our index. This is whatever index of the array we are currently looking at, our current sum. This is the sum of the subsequence that we've considered so far up until this point, and the current length is the length of the subsequence that we're currently considering. So if we get to the end of our array and our current sum equals k, then this is a valid case. So we want to do the logic that we talked about before, where we return 2 to the power of the length of nums minus the current length of our subsequence. Otherwise, we're going to return 0 because we know that this current subsequence will not contribute to our solution. This is another optimization, and this is what allows us to bind our time complexity to O of n squared times k. If we didn't have this, this would actually be an n cubed solution. So having this here slightly optimizes. And we know we can do this because if our current sum is greater than k, our array only has positive integers. So there's no way we can ever get any lower. So if we reach this point, it's kind of a terminal state for our problem, and we can just return 0. So here is where the actual O1 knapsack logic takes place. So we're going to simulate 2 cases. So we're either going to include this element in our current subsequence, and what this looks like is we're going to move on to the next index in the array. To our current sum, we're going to add the current number and then increase the length by 1. If we don't take this element, we're still going to move on to the next number, but we're going to keep our current sum and our current length. And then since we want to find all the possible combinations, we want to actually return the sum of both of these options. Then at the end, we're just going to call our recursive function here with our 3 initial arguments, all being zeros, initial index, initial sum, initial length, and we're going to mod this by 10 to the 9 plus 7. So let's just run this and see if it works. And it does. So yeah, this was a really interesting question. Pretty tough, but definitely a lot to learn from. So hope you enjoyed it, and thank you for watching.